All right, let me introduce Theresa Foley, coming from NVIDIA. They're going to here to talk about the Slang shading language. Please take it away.
All right. Hi, everybody. I'm Tess. So I'm going to talk about some of our experience with the Slang shading language. A lot of folks in the room actually probably I've worked with or known before, but I just want to start by giving a little bit of a background on like who I am, because I'm about to say a contentious thing on the next slide, and I want to set up that I have the bona fides to set it. So I've been involved in like GPU research way back when. I was part of CUDA 1.0, did my PhD on some shading language work. I've been at various companies in the industry and also been involved at Khronos on the specs for OpenGL, SPIR-V, and Vulkan. And currently what I do is I'm the tech lead and manager for the Slang shading language at NVIDIA. And really my job is to try to make sure that our graphics developers inside of the company have the best tools possible and unblock innovation. And what I want to say here today is Vulkan has a shading language problem. There are key challenges the developers are facing that are not being addressed by GLSL or the alternatives out there. I think there's some other speakers that are going to be talking tomorrow who probably agree with me on this. But I want to highlight a few of the specific challenges that I think we're facing as developers that need to be addressed by our tools. So I have three main points here and one bonus one that people might not have thought of yet. So the first of these is that there's an increasing scale and complexity of shader code bases, right? We designed the initial GLSL language and things like that to handle code bases where we had maybe tens of lines of code in a shader, and now you're having game shader code bases that are tens of thousands of lines of code, and the languages haven't scaled. Another point here is that the Vulkan API and SPIR-V are rapidly evolving and innovating, but there's really been no time taken to evolve the language fundamentals, right? That there's always a new extension to be put in, but not a lot of work to improve quality of life features in our programming languages. And another really big problem here that has been kind of on my mind for several years now is this shader combinatorics problem. We all hear about it. Game developers complain about it constantly, that they have to generate thousands or even millions these days of permutations of their shader code to deal with different rendering configurations. And this affects compile times, binary sizes, load times, and things like that. But we really haven't been making enough progress on this as an industry, right? It's a persistent problem. And it seemed like the compiler and language tools are part of the problem and maybe need to be part of the solution. And then my last little bonus challenge here that maybe folks have not largely thought of, but strangely enough, someone from NVIDIA is going to talk about, is the intersection of machine learning and graphics, that we need to be able to be ready for what machine learning is going to imply for real-time rendering workloads. Right? And another part of the context here for why we have this problem is that evolution on GLSL seems to have stalled. Right? That when I was involved in things for Vulkan 1.0, it was out of scope to put major changes into the shading language to support a new API. We wanted to get a new API done. And so the choice was made to retrofit Vulkan support onto the existing GLSL language. And then also part of that time frame was the introduction of SPIR-V. And there was a very explicit intention there to free the Vulkan working group from the responsibility for doing language design in the long run, right? We wanted the API design experts to do the API design so that language experts could do the language design. And it didn't really seem to evolve from there. Like nobody picked up the ball. Right? And I don't put that on the Vulkan working group because we were supposed to be designing the API. But there is a bit of a chicken and egg problem here that we faced, I think, that the Khronos model has given us, which is that developers at large don't want to adopt new language features in something like a shading language unless those features work everywhere, right? Including on their minimum viable platform, right? Their min spec. And they need those features to provide some kind of immediate benefit, or else why are they rewriting any code to use them, right? But on the other side, if you look at most of the influence that IHVs bring to something like Khronos and to an API like Vulkan, most of the time we're interested in showing off some new feature we have. We want to differentiate and we want to compete. And so we're more interested in exposing what the latest GPU can do than in floating all boats and introducing quality of life features. And so that tension there is part of where the project I run called Slang started from, was that we really wanted to address these big challenges in shader development head on, because at the end of the day, we also have developers in-house at NVIDIA. We're not just making the hardware, we also have people doing software. And when they see these same challenges, they come and complain to people like me. So at a high level, the Slang project, what I'm working on is really just a cross-platform shading language. And it's trying to move very fast, keep pace with the future of real-time rendering. So it's an open source project. It has backends to support a lot of different APIs, including Vulkan. We currently have the compiler support backwards compatibility with existing HLSL code bases using the feature set of HLSL 2020 and earlier. There's some things that have been added since then that we're not perfectly compatible with. And we are also currently working on support for GLSL so that we could take an existing GLSL code base and kind of slangify it by adding some of our newer language features on top of those code bases. We're in the process of working on supporting a couple new APIs, but those are not ready yet. But it is an open source project, and so pull requests welcome, all that usual stuff. But a lot of our original motivation for starting this project was brought about by developers inside of NVIDIA who have to do graphics software day to day. And what they were telling us is that they need to build larger and more complicated rendering code bases, and they wanted to be able to use more modern software development techniques, right? They wanted kind of a grown-up language for graphics. So one of the things that Slang brings to the table is a more advanced type system and a more advanced language with a lot of systems, a lot of features inspired by Rust and Swift and C# that our developers might be familiar with, but that also are not something they've used before in GLSL or HLSL or other shading languages. So there's a quick list here. I'm going to go into detail on some of these, but Slang brings a proper module system with visibility control. We also have a system of generics and interfaces, which I'm going to dive into in a lot more detail. We have things like associated types and associated constants that like the Rust and Swift folks in the room will probably understand what I mean. And then we also have just kind of a grab bag of other language goodies that we've all kind of gotten used to in our CPU programming languages and haven't really been seeing come to shaders in a while. So I'm going to go through a couple of these in detail just to give a feel for like what day-to-day programming in Slang feels like compared to what people might have been used to in raw HLSL or GLSL code bases. So again, we have support for modules. So in this really simple example here, on the left, we have a module full of material code that someone might have written. And then on the right, if I write a module for dealing with my scene, I can import that module from materials, but I actually do have visibility control. I can rely on the public interface of this module, but not on the implementation details of it. And I will actually get compile time errors if I try to use things that I'm not supposed to be aware of. And this allows us to scale up and work with larger teams, right? It allows you to define the interface to the subsystem you're responsible for and not worry about people relying on implementation details. Really small stuff that we just know we want in our languages. There's a very similar motivation for having explicit interfaces in the language. And so this is something where, again, the Rust folks out there probably know that they use traits all the time to write their code. Swift has a similar feature, and all of these are really just copy-pasted from type classes in Haskell, if any like really hardcore PL folks are out here. But basically, a way to make the interfaces, the requirements of your types explicit, right? These are the things that all materials in my framework must provide. They all must be able to be sampled at a point and produce a BRDF. And that BRDF better be a thing that I can call an evaluate function on to evaluate the BRDF at a particular incident and excitant angle, right? So interfaces are used heavily in sort of Slang code to help us build up libraries of different material effects, different reflectance functions, different lighting techniques. And then the system has support for generics. So in this example, we see someone writing a lighting function that is generic on a type M that is constrained to support the material interface. And what we see is that by writing in terms of explicit interfaces here, not just something like templates, is that the Slang language can provide things like autocomplete support while a developer is writing this. So that's what you're seeing on the left side there. And then also on the right-hand side, you can see that unlike what you might have if you use preprocessor-based techniques to combine your material and light shaders and things like that, the compiler can give us a static error by saying, hey, you tried to use something not defined in that interface. Not all materials are guaranteed to support this method that doesn't exist, whereas some specific material implementation might. And this stops you from making mistakes where maybe you bootstrap a subsystem using particular material and particular lighting effect, but don't realize that you're not sticking to the canonical interface that your framework or engine requires for those, right? You might use facilities that are specific to this light source and not scale to others. Now, generics, I just mentioned preprocessor specialization, and that's a lot of the motivation for why we added them to the Slang language. So you can start thinking of them as a more principled alternative to the kind of preprocessor-based specialization that developers have been doing for a long time. So on this slide, we see on the left some code written using that generics feature in Slang, and on the right, we see a more canonical, like preprocessor-based way of doing the same kind of thing in HLSL, where we might have a cascade of conditionals to handle each of the different material types we want to support. And what I want to hit on this slide is that we can compile these two things down to code with the same performance, right? So the cleaner code on the left can compile to the same statically specialized code as what's on the right. But what's even more important here when we talk about things like that shader combinatorics problem is that generics, unlike something like templates, actually have a lot of flexibility in the language semantics. It doesn't dictate that we compile it this way. So in fact, the Slang compiler has support today for taking code, like on the left side of this slide, and compiling it, setting different compiler options to generate kernels with different performance trade-offs. So for example, we can take that code on the left and plug in a single material implementation and generate statically specialized code that will only work with exactly that material. We can also give the compiler a list of different material implementations, and we can automatically synthesize what people often refer to as an Uber kernel, right? A switch-based branchy kernel that is keying off of tags to dispatch out to different shading code for different material types. And so in this case, you can actually generate a dynamic branching version of things that handles a subset of your material types, right? And that may be a different trade-off in terms of compile time versus runtime performance. You may be sacrificing some amount of runtime performance by introducing branching, but spend less time compiling because you're generating one shader variant instead of n. And then finally, Slang already has support today for generating true dynamic dispatch code from this same input on the left. So on platforms that support function pointers, things like CPU, CUDA, and eventually we'd like to support this for Metal, where there are native function pointers supported in the GPU code, we can generate dynamic dispatch logic, and then a single version of this code can work across all material types, right? And again, there's going to be performance consequences to doing something like this, but it is a trade-off that we want developers to be able to make. And so this has been a little bit of a whirlwind tour of like high-level language features that we just threw in here, but I want to emphasize that these were things we did because the developers inside NVIDIA have been using this thing. So a lot of the rendering infrastructure inside of NVIDIA is already using Slang as the shading language. So the Omniverse project uses Slang to implement its real-time path tracing renderer. The Omniverse Kit application uses it. The Portal RTX remake uses Slang as the shading language for its rendering logic. And also the RTX Remix project we put out that lets fans create ray traced mods for the games they like, uses Slang as the shading language, and also our real-time rendering researchers inside NVIDIA use a framework called Falcor, which is a real-time path tracer that is implemented using Slang. And so these developers in-house are making heavy use of things like interfaces and generics that have kind of been highlighted on this slide. These are copy-pasted chunks of code outside of our code bases. And they do this to help build larger and more complex rendering code bases while still keeping them maintainable. Because we're doing a lot of things with real-time path tracing at this point, and we're finding that you scale up a lot in complexity with different lighting methods, different sampling strategies, and so forth. And so this has become really popular for the projects that use it because they can get this kind of benefit to software development practice without compromising performance. So I want to really hammer on this point here that the Slang is being used by the Falcor project in NVIDIA research when they started doing work on real-time path tracing. And they ended up using some of our language features, like I just talked about for generics, of doing dynamic dispatch and switch-based Uber kernels and things like that. They're using these advanced language features in the inner loop of their real-time path tracing code and in still achieving exceptional performance. And that path tracer developed in NVIDIA research in Slang is the prototype that led to the first AAA path trace games out there, like Cyberpunk Overdrive and Alan Wake 2. So this code base was used to demonstrate the viability of real-time path tracing, and it didn't compromise on software development process and modularity. So you can actually have both. All right. We're not just concerned about current problems, though, because we also think that machine learning is going to be a valuable tool in the toolbox of real-time graphics developers. So I'm going to come here and say, you need to learn some machine learning, even if you plan to just do graphics. And I want to emphasize, though, that when I say machine learning, it's really helpful for those of us in the graphics community to realize that a lot of that just means gradient-based optimization. Like, it doesn't have to be a scary other discipline that we don't really understand. It's really just another tool for solving some of the hard problems we have in graphics. Things where we want to approximate or tune parameters, it's a useful tool to have in our toolbox. But what we found when we tried to integrate machine learning into rendering applications that were being done by real-time graphics developers was that most of these developers would rather write code in a shading language than in your typical machine learning frameworks, right? It's hard to take a graphics developer who loves writing GLSL or HLSL and tell them to write Python suddenly. And that's not just a language difference. It's also a difference in the kind of code we write. right? Graphics shaders very often have divergent control flow and things like loops, and they aren't really written in a style that is compatible with this more bulk synchronous tensor model that a lot of the Python frameworks use. And so we realized that we needed to bridge this divide and adapt to what our developers actually wanted. And so that is why the Slang language also has first-class support for automatic differentiation built in. So this is something where you can take your existing code bases in HLSL, and soon this will also be supporting for GLSL, and add a few annotations to take your existing code and say, this should support differentiability. All right, so in this very simple example, somebody wrote a function to square a number, and they marked it as being differentiable. And as a result, in the main function down below, they can use this built-in operator we called backward diff. I'm not a fan of that name, but hey, that's not my job right now. It's basically a higher order function that takes a shader function and turns it into the backwards differential form of it. And we can apply that to evaluate that at a specific tangent vector and parameter value. And so this just works for existing Slang code. It can you can throw it on other functions. And I want to emphasize here today, again, I wonder if there's graphics developers out here like thinking I'm just making stuff up, and I want to try and give some examples of where automatic differentiation and machine learning apply to more problems than you think, right? Even some very traditional graphics problems can benefit from using these new tools we have in our toolbox. And so I'm going to use two examples that are just very common things we do, things like generating bitmaps and trying to do texture compression, right? So if we think of bitmap construction, in this case, we have our textures that were artist authored, right? We have some albedo, normal, and roughness, and we're going to try and generate bitmaps from them. And we have traditional techniques we might do where we progressively average down quads, but those don't actually lead to great rendered quality. They don't really average the appearance of the surface as they produce the output. So what we really want is appearance-aware bitmap construction, which would mean that the lit result of our material should look the same or as close to the same as possible with our lower detail MIP levels as with the full detailed ones, right? So we really are just saying, I want to minimize the squared error between my low res MIP levels and my high res MIP levels when I render them, not just the images themselves. And that means we can really just phrase this as an optimization problem where the content of our texture is the parameters we want to optimize. And if we have the ability to render those, which is the shader code we already wrote, we can then get gradients by using automatic differentiation and then just iterate to converge. And we can get the ideal appearance preserving bitmap hierarchy without having to write any additional code. So to be really clear on what that means in practical terms, again, for this specific example, here is some of the actual code that got written for this. Where on the far left, we see the material evaluation logic for this example that's all written in Slang. And all that the developer had to do in this case is add that annotation to the top to say, hey, I'd like to be able to differentiate through this code, right? They didn't change their code to avoid the branching in it or loops or anything like that. They just wrote pretty ordinary shader code. Then they also had to define their loss kernel, which is not that hard to do. It's really just saying it's the mean squared error between the original image and this lower res version once we render out the results with lighting and everything. And then the Slang project, we added support for allowing shader code written in Slang to be imported into Python-based machine learning frameworks like PyTorch. So you can see in the far right example, we're directly calling this function BRDF loss that was written in Slang in the middle panel here from our Python code. And therefore, we're able to integrate all this Slang code into an otherwise Python-based learning app and produce those bitmap hierarchies, right? So for a second example, of where you might be surprised to find that automatic differentiation is a useful tool. We can also frame something like texture compression in terms of this. For those who aren't very familiar with block compressed texture formats, something like BC7 mode 6 here, all we're really saying is that for every 4x4 block of texels, the compressed format stores 2 endpoints in color space, and then each texel is a linear interpolation coefficient between those two, right? So it's just a couple of parameters, and we can just treat the compression of a texture block as an optimization problem. Again, those are the parameters we want to optimize for. And so this means we can actually write a texture compressor without ever writing a texture compressor. So the recipe here is pretty simple. Step one is write a decompressor, and that's actually the easy part. Anybody who's done texture compression knows that the decompression side of things is the easier side. You implement your loss function, which again is just gonna be like squared error between the original image and the result of decompressing the compressed image. And then you can actually just write your gradient descent optimization pass as an ordinary loop in shader code, right? You don't even have to go to any fancy Python frameworks here or anything like that. It's really, gradient descent is just a very general optimization technique. And what we find is that using that kind of technique exactly there, we can first write our decompressor and get our compressor for free. And it actually runs the full optimization loop within a single shader invocation. You're not doing a bunch of compute passes or anything like that. And so we can actually get a very fast compressor without ever having to write it in the first place. So these kinds of benefits of integrating machine learning techniques into rendering code is part of why we've taken that Falcor rendering code base. This is the open source rendering code base that NVIDIA's real-time rendering researchers use, and they've made the majority of that shader code base differentiable. So they took a shader code base written in Slang that's been developed over more than 5 years. It's more than 5,000 lines of Slang code for the path tracing logic that they're using here. And with about 200 lines of annotation, they were able to get full differentiability through the path trace results. So here we see an example of a primal image that was rendered, and then the derivatives of that with respect to camera position produced automatically. So this has been a whirlwind tour of what we've built in this thing. And the reason I'm here talking to everybody here today is we're starting to think that maybe Slang is something that's ready for the Vulkan community to start engaging with. So we've had some practical experience on that recently that I'm really excited to be able to talk about, which is that we collaborated with Valve and we're actually able to migrate the shader code base for the Source 2 engine over to Slang. So Source 2 is the engine used by games like Dota 2 and Counter-Strike 2. It targets both Vulkan and has a fallback path for D3D11. And then the editor, the Hammer editor, actually uses Vulkan ray tracing as well. So the shaders inside of this engine are written in HLSL, but also make use of Vulkan-specific extensions. So things like subgroup ops and ray tracing, and also some use of bindless. So we're talking about several hundred individual material files, like VFX files, for those who are familiar with the source engine. And these things compile down to produce over 10 million different shader variants. So again, there's this shader combinatorics problem I was just talking about. So the shader compilation pipeline at the time we engaged was that on Vulkan, the project was using DXC plus SPIR-V opt and SPIR-V reflect to get parameter binding information. And then on DX11, it was just running through FXC. So the motivation for engaging on this was a concern coming from Valve that they wanted to be able to adopt state-of-the-art Vulkan features and hardware features sooner than was being possible on their DXC-based compilation path, right? There were things that they wanted to have accessible that were added to Vulkan, but weren't yet being exposed to the DXC code base. And so they hoped that by engaging with the Slang project, where we can directly generate code for SPIR-V, bypassing things like the DXC code base, they could adopt things sooner. So things like support for buffer device address, which we expose as this const buffer pointer type. So we worked together with them, converted the entire HLSL shader code base to work with Slang, and kept the existing optimization pipeline after SPIR-V generation. So Slang is being used to compile down to SPIR-V, and then some existing SPIR-V tools are being run after that. And in practice, this only took about 10 lines of actual code changes to fix issues in their code base that were leading to incompatibilities between the Slang compiler and the version of HLSL they were writing in. There are additional things that were fixed along the way for code quality reasons, where our compiler identified certain uninitialized variables and things like that that weren't being detected by their existing compilation path. And so as it stands today, Valve is talking about moving the Source 2 shader compilation over to Slang. And so that prompted us to say, we should probably be talking to more Vulkan folks about this thing if this project is working. So it's worth noting that we really think of Vulkan as one of the top tier platforms we're supporting with the Slang compiler. You know, I showed a bunch of different platforms on that first slide, but it's worth noting that we're not treating it as a fallback option compared to some other API or picking some lowest common denominator. Our philosophy on the project is that we want to make sure that as new features show up in Vulkan, we have a way to expose them in our shading language. And that's true even if they're Vulkan-specific things. We would like to be able to expose stuff that is only on Vulkan and not yet on other APIs, and just let people write Vulkan-specific code in our language. We're not trying to produce a write once, run everywhere solution necessarily, so much as a solution where you write code that uses a certain set of GPU features, and it will run on the platforms and APIs that support them. And so if you want to write Vulkan-specific stuff, we're here for it. And along those lines, we've added a number of Vulkan-specific features to the Slang code base over time. So the top left here, we do support combined textures and samplers, which is something that's in Vulkan, but not in a lot of other current APIs. We support buffer device address. That's in the bottom left here. We're going to keep working on improving the syntax for that, but we do have this ability to store pointers into constant buffer address space within your ordinary struct data. We have direct support for shader storage buffers. And then we also in the bottom right here have our own syntax for sticking sphere v assembly directly into your Slang code for the cases where you want to access something we have not yet added to our standard library of GPU functions. All right. So wrapping up, I know I've been going very quickly here, but I want to try and make the point that we think Slang might be ready for the Vulkan community to engage with. We've built a really fast-moving language that we think is aimed at the future of where real-time rendering is going. It's being used to enable our in-house developers who use Vulkan to innovate and build more complicated rendering applications than ever before, but we're also continually evolving it based on their feedback. Right, so it's a system that supports Vulkan and Sphere V as a first-class thing. We are continuing to evolve and add things to it based on the needs of Vulkan, not just treating it as a second-class thing to some other APIs. And we think we've gotten to the point where we have an easy path for adoption in existing code bases, right? Our experience with Valve shows us that our on-ramp from HLSL is pretty easy, and we're actively working now on trying to provide an on-ramp for developers who have existing GLSL code that they might like to bring toward the future. And so my main reason for coming and speaking to you all today is that we want to start hearing from the Vulkan community. Like, we want to understand what other programming challenges people want to see addressed in Slang or other shading languages. And then also we want to encourage people to try and kick the tires on this thing and start giving us some feedback on it. So thank you everybody for listening.
All right, I see hands. Hopefully we're able to get to as many questions as possible.
So, hi, and thank you for this presentation. Very exciting. I said yesterday that high-level language support was something that keeps me awake at night when I think about the future of Vulkan. So this kind of work is very exciting. And of course, you have spoken to the working group before. I think I've always admired the way you have been able to evolve this language while it's being heavily used by a lot of projects inside NVIDIA and now apparently outside as well. And I mean, that if people are going to bet their future of their project on the platform, you have to give them stability guarantees. And so I'm kind of wondering, but on the other hand, you have to evolve the language and that takes work and you have to do experiments. I'm just wondering, how do you do that?
I think for up till now, we've kind of done it by the seat of our pants is the honest answer there, is just by working really hard. But as you start to scale up with more and more interested parties, that becomes less tractable. And so I will say we're trying to figure out what that looks like going forward. And that is also part of the conversation we want to have, is like, how do we make a project like this meet the needs of a large number of developers without slowing it down also? Like, how do we evolve and not end up stagnating like some other solutions have? But also not end up, we don't want to produce something that only we use because we are putting a lot of effort into it and we think others could benefit. So figuring out the model is something that we would like to talk about, of how we evolve this.
I could ask questions for a long time, but I bet other people want to ask.
And you and I can talk after this also.
Yeah.
Okay, so I obviously have like lots of questions as well, but I'm just gonna try and narrow it down to two. I've seen some samples here, right? And none of them seem to have like an in-out parameter. I was just thinking about asking, what's your calling convention? And do you have reference or pointers, to return modifications to variables other than the return value?
Okay, so the easy answer there is because we are backwards compatible with HLSL, it also has an in-out parameter passing convention, very similar to the GLSL one, and we support that. In terms of spec behavior, that is a copy in, copy out behavior, and that is what we implement on targets that don't support references. But we can get into the details of that. Developers very often want by reference parameter passing, especially const references. And so there's some subtlety there where if you want to get into all the nitty gritty of that, I can explain to you why we think we're able to thread the needle and support both very cleanly, but it's hard to Rust has borrows, and that would be the answer that most people need to hear, is that borrowing semantically guarantees unique access and therefore means you're actually agnostic to whether it's copied or referenced. And so I think we have an answer for you, but the short answer is yes, the in-out keyword works.
All right.
We can talk more.
So can I use this on Android?
We have at least a Linux build. I haven't tried out, I don't think anybody has run it on Android yet as part of our continuous integration right now. So I speculate yes, but I'm sure problems will arise and we should add it to our testing if we want to make sure that doesn't regress. So that would be great. We should make that happen.
We see more hands. It's okay if we go a little late.
You talked mostly about graphics applications. Are there any compute applications that are using this?
Honestly, a lot of the graphics applications I've been talking about are primarily written as compute shaders. Once you start writing these big path tracing code bases, there's not a big difference based on whether your whole thing runs as a giant RayGen shader or your whole thing runs as a giant compute shader. And so it's 6 of 1, right? There's plenty of compute code running through this, but we intentionally aren't thinking of this in cases where you're almost leading. This is not a solution to the problem some developers have of, hey, I have all this like OpenCL C++ and I want to run it on Vulkan. We're intentionally not attacking that problem insofar as the developers we're talking to already have HLSL or GLSL and are already working within the constraints of those languages. So the kind of compute that current Vulkan developers write is what we're targeting today.
Thanks.
Unless there is more. Oh, 2 last questions, then I'll be it. Ken, you'll be last.
If I understood correctly, you managed to use Slang for the source to code base, changing barely anything. And the other aspect is solving the problem of having millions of shader variants to be generated. And the way I understand that you are fixing this issue is basically by paying a cost dynamically at execution time instead of compile time. So if you change barely anything with the Valve code base with source 2, can you give us an idea of the time it takes to generate of the shader compared to the previous stack, just to have an idea of the performance, we'll say, of your
I see. I don't have
compiler.
performance results here. Just to be clear, in that case, if you take an existing HLSL code base where you were generating 10 million variants with preprocessor-based techniques, just switching from you calling DXC to calling Slang C as your compiler doesn't change anything about that. So you're still generating those 10 million variants. Our compile times are something we've worked on a lot. And the main thing we aim for is that the actual source to SPIR-V compilation time should be negligible compared to the driver compile times that you after SPIR-V. But we can't really pretend that we don't add some compilation time compared to some other tools based on the advanced language features. It's just not in the same ballpark as driver compile times. But if somebody wants to get any of those, start exploring that trade-off space that I was talking about between compile time versus runtime performance using generics, you need to start actually adopting these more advanced language features. It's not just take your existing code base and throw it at a new compiler and magic happens. So the harder process once a developer gets onto something like Slang is thinking about what is the software architecture you want to have for your rendering code and starting to build. And we try to make it so that you can get your foot in the door just by throwing your code at the compiler. But if you want to get the real benefits, you're going to have to start evolving your software architecture over time. But we'd rather you do that gradually than have to do it all at once.
Okay, thank you.
Forgive me for not just looking at your GitHub repository, but does your team think of your tool as more of an offline compiler or one that would be dynamically linked into an app and invoked at runtime?
We definitely have a DLL-based API that we can use for compiling at runtime, and there's a lot of functionality to it that is actually easier to access through the API rather than from the command line tool, just because once you start getting into some of those interesting compilation trade-offs and specializing generics and things like that, you're doing manipulations on code that get cumbersome to specify with just tons and tons of command line options. So we strongly prefer folks integrate via the API rather than the command line tool when possible. We think you can get better results. Yeah.
Okay, and with that, we're going to cut off questions. Another round of applause.